Hello everyone, welcome to the last set of 5 questions, 5 organic questions from the JAM 2022. So let's start solving by the first question. The first question says zinc containing enzymes is or are carboxypeptidase, carbonic anhydrase, hydrogenase, urease. So now this you have to remember, there is no way of understanding anything. So the thing is, in carboxypeptidase and carbonic anhydrase we have zinc, whereas in hydrogenase nickel and iron is present, and in urease nickel is present. Okay. So next question, among the following the number of aromatic compounds is, so we are having quite a lot of molecules and is asking which are the aromatic molecules. So for a molecule to be aromatic it needs to fulfill the following rules. First, it should be cyclic. All of them are cyclic except this. So this we can rule out immediately. It should be conjugated. Now what is conjugated? Conjugated means all the neighboring atoms in the cycle, in the system which you are considering, should share the portion of electrons. The electrons should flow through all of those atoms. That means each of the atoms should have a unhybridized p orbital. Now that p orbital might have electrons, might not have electrons, so it may have just one electron, it might have two electrons, and sometimes in heteroatom it is not even a p orbital, but it should overlap with the rest of the orbitals of the ring. So let us see something like look at this molecule B. Molecule B, this carbon, the valency of carbon is 4, should have 4 bonds. So 2 bonds you can see in the part of ring, 2 bonds are joined with hydrogen. So all the carbons are sp3 hybridized. There is no unhybridized p orbital. But if you see here, this carbon has a pi bond. That means this carbon is sp2 hybridized. It has 3 bonds, sp2, it forms 3 bonds, and there is a p orbital which has 1 electron, and that p orbital is overlapped with the another p orbital of the neighboring atom through 1 electron. So we can rule out B from this. Which else can we remove? Now this is very interesting. See, now see this molecule, there is a pi bond, so these two p orbitals overlap. Here also there is a pi bond, so these two p orbitals overlap. So because this is neighboring, this p orbital also overlaps with this p orbital, this p orbital overlaps with this p orbital, this p orbital overlaps with this, and then we have to find out, does it overlap with this? So there is a carbonyl group. So very clearly there is a p orbital here, and oxygen also has a p orbital, and that means both the carbon and the oxygen are sp2 hybridized, and therefore they have vacant p orbital and they overlap. So how an orbital can, which has who is overlapped with another atom, will overlap with this ring also? So if you see here, the evidence is seen by the polarity of the molecule. What they have observed is, this molecule is highly polar. Oxygen has lot of negative polarity and the ring has lot of positive polarity. So very high dielectric moment is there. Okay, very high dielectric moment is there. So the reason being is, the oxygen takes 2 electrons, so that p orbital is vacant. So that vacant p orbital we are showing as positive charge, and that overlaps with the, and that vacant p orbital overlaps with all the other p orbitals, and which I have shown here. And you can show through simple conjugation. This comes here, you get positive charge on this carbon, then it comes here, that comes here, and you get something like this. And therefore this is aromatic system. Let us not talk about aromatic system, but what I am saying is, this is conjugated system. Similarly, this is also conjugated, this is conjugated, this we have already removed because it is not cyclic. Let us look at this molecule. Now this molecule, what happens? These 4 carbon atoms have pi bonds, so they have overlap. This oxygen is having single bond, so it is sp3 hybridized. So it has another sp3 hybridized orbitals, rather 2 sp3 hybridized orbital, and both of them have lone pair of electron. Now this lone pair of orbital overlaps with this, so the only this orbital does not share 2 electrons. It is being shared by all the p orbitals which is part of the ring. Okay, all the p orbitals which is part of the ring. So this is also another conjugated system. I'm sorry, I'm not able to draw this very properly. Yeah, And let us look at the next molecule. Even this molecule has nitrogen. Nitrogen has lone pair of electron. So this this is again not p orbital. It's a sp3 hybridized orbital, but contains lone pair of electron that overlaps with all the p orbitals of the ring. So this is again conjugated system. Here there is actually negative charge, means it is sp3 hybridized, not a p orbital. So this is again orbital which has lone pair of electron, which overlaps with the pi bond, a p orbital here and the p orbital here, basically with the pi bond. So this is again conjugated system. Here there is no need to explain, because all the, we can see all the neighboring atoms as a p orbital, and therefore pi bond is formed. Similarly this also. This one is not. Why not this one? Because see, this atom, this atom, this atom, this atom, this atom does not have pi bond. So this is not conjugated. Similarly here also is not conjugated, here also is not conjugated. So I can rule out L, and I can rule out B, and I can rule out G till now. And the last one, it says it should follow Huckel's rule. That is, number of pi electrons taking part in conjugation should be equal to 4n plus 2, where n is equal to 0, 1, 2, 3, 4. What it says is n can be any number, it can be 0, 1. So when n is equal to 0, so what happens? 4 into 0, that is 0, plus 2 means 2 electrons. When n is equal to 1, so 4 into 1 is equal to 4, plus 2 is equal to 6. Similarly, if you put n is equal to 2, you will get 10. So if the number of pi electrons which are conjugated, if it is if there are 2 electrons or 6 electrons or 10 electrons, then we will say they are following Huckel's rule, that is 4n plus 2. Otherwise it is not aromatic. And let us look at them. So let us look at this one. So how many electrons are there? 1, 2, 3, 4, 5, 6, 7, 8. So each pi bond has 2 electrons, since 4 pi bonds, so it is 8. So it rather follows what is called as 4n rule. 4 where n is equal to 2, so 4 into 2 equals to 8. So when a system follows all the other rules of aromaticity, that means it is cyclic, conjugated, planar, but it has 4n number of pi electrons, then it is anti-aromatic. Okay, anti-aromaticity is explained through molecular orbital picture. Basically it is very unstable. So molecule rather remain non-aromatic rather than being anti-aromatic, because it is not aromatic. So what it does is it loses its planarity. So one of the important thing which I think I skipped while telling, the molecule should be planar. When it is planar, so that the p orbitals are in the same plane, they are parallel to each other, and so they overlap, something like this. So this p orbital and this p orbital, if they are parallel to each other in same plane, then only they overlap. For that to happen, should be planar, right? So what molecule does? It loses its planarity, it becomes puckered. When it becomes puckered, what happens? The orbital stops overlapping to avoid the anti-aromaticity. And how can we know this? When a system is aromatic, something like benzene, when a system is aromatic, so if you measure the bond angle between any carbon, between any two carbon atom, you will see that bond length is same. So this bond length and this bond length is same. That means there is no alternate single and double bond, but it is conjugated, it is all overlapping, and therefore they are all equal. But here, because it is different, you see, so what happens? This is double bond and this is single bond, and it loses planarity to avoid conjugation, and then you can see that single bond is actually longer than the double bond, and you can observe that throughout the ring alternate longer bond and smaller bond is seen. So very clearly they exist as simple alkenes without any conjugation, right? This we talked about. So how many electrons are there? So the pi electrons has come on oxygen, so this is vacant. So number of electrons which is part of conjugations 2 plus 2 plus 2, 6. So this is aromatic. Okay, let us see about this. What happens here? So 2, 4, 6, 8, 10. So this is also conjugate, this is also aromatic. Here again 2, 4, and the nitrogen has lone pair of electron, that is part of it, so it is 6. So this also, this furan also, it has 2 electrons, 2 plus 2, 4 plus 2, 6. So this is again 6 electrons. This is 4 electrons. this is 4 electrons, so it is anti-aromatic. Okay, it follows 4n rule. Again this will lose its polarity, and you can see that single bond and double bond will be different. And this is again 4 electrons, 1 2 3 4, so this is not aromatic, this is rather anti-aromatic. Here it is 6 electrons, here also it is 6 electrons. So number of aromatic systems are C, D, E, F, J and K, that is 6. So the answer is 6. Okay, moving on to the next question. It says the number of stereoisomers possible for the major product formed in the reaction is. So you are having this molecule, it says how many stereoisomers are there. You are adding one equivalent of HBr. So one equivalent of HBr will add to only one of the double bond, either this or other one. So basically pi bond will move and pick up proton. It will pick up in such a way so that you get a very stable carbocation, and that will happen on this carbon, because when you give this you are getting a benzylic carbocation. So a carbon having a positive charge next to its phenyl ring, this is very stable. Why it is stable? Because of resonance stabilization. Because of resonance stabilization, you can see here you are having a positive charge here, and you are having double bond, double bond, double bond. So this can overlap here, this comes here, and you get positive charge here, then this moves in. So the unstabilization is because of the positive charge. So if only this carbon has positive charge, it is very unstable, to want back electrons, so it is not stable. But so many electrons come and share the burden of the loss of electron, so it's quite stable, benzylic carbocation. Then the Br comes and attacks here, and you get this. Now you see these two hydrogens on the terminal carbon, both are hydrogen, so geometrical isomerism is not possible. If one was hydrogen, one was something else, then E and Z possibility is there, so you can avoid any kind of isomerism possible there. So only one chiral center is there. You see here there is one chiral center, so you know we can have 2 to the power n number of stereoisomer. So 2 to the power n here is 1, so it will have 2, that is 2 enantiomers are possible. So you can see here I have made one hydrogen away from the viewer, Br towards the viewer, and here I have changed it, so these two are 2 enantiomers. So the answer is 2. Next question is number of signal observed in proton NMR spectrum of compound is. So this is the molecule, very symmetrical molecule. So whatever happened one of the ring, whatever signal seen, that same signal will be seen in second. So these two carbons attached here, there is no hydrogen. You come next, here also no hydrogen, here also no hydrogen, right? All these are identical, chemically identical, in chemically identical environment. Now this methyl has exactly same environment as this methyl. Similarly, this methyl and this methyl also has same environment, and all four are in chemically identical environment. You can see here, when you move from methyl one bond, you get a carbon, you come down, you get another carbon, you get another carbon. When you join, you can see that they both are leading to same. Similarly, if you move 2 bonds, you see a methyl. Similarly, here also if you move 2 bonds, you see a methyl. So these 4 methyls are in chemically identical environment, and they will show one kind of signal, a single signal. Okay, and when you move to next, so here there is a hydrogen, here there is a hydrogen, right? So these two are again identical, these two are again identical. Similarly, these two hydrogens are also identical. So you get this bond. Okay, so this will show second signal, and then this CH3 and CH3, they also show third signal. So the number of signals should be 3. The last question says the reaction of 122 grams of benzaldehyde with 108 grams of phenylhydrazine gives 157 grams of this product. So it is asking what is the yield of the product. So first let us write the reaction. The reaction is this is benzaldehyde. You react it with phenylhydrazine. So phenylhydrazine is NH2. So you know what happens, H2O is lost, basically H2O is lost, double bond goes and attacks this nitrogen, you get this product. So it says what is the yield. So yield you have to always find out from the limiting reagent. So let us find out how many moles. Never go by mass, always find out moles, because mass is not the correct equivalence. Equivalence will be always by moles. So find out how many moles of this benzaldehyde is there. So benzaldehyde, first you have to find out molar mass. So molar mass, I hope everybody understands. So 6 carbons are there, 7 carbon, and so 12 sevens are 86, right? And plus 16, and then you have to add 12 sevens are 84. I'm so sorry. Yeah, 12 sevens are 84, plus oxygen, that is 16, and then 5 plus 1 6 hydrogen, that will add up to 106. And similarly phenyl hydrazine, you will get the molar mass as 108. So the moles of benzaldehyde is equal to mass by molar mass, that equals to 1.15 moles, and moles of phenyl hydrazine is 1 moles. Okay, so we can see that for the reaction we need one equivalent of this, which reacts with another equivalent of this to give one equivalent of the product. Now I am having little more of benzaldehyde, so some amount of benzaldehyde will go unreacted, that is excess, and limiting reagent is phenyl hydrazine. So what we expect is from 1 mole we should get 1 mole of the product. So let us see what is how many moles of product is formed. Again mass by molar mass, so you get 0.8 moles. We know that we are starting with 1 mole of limiting reagent, so you should get 1 mole of the product, but what we are getting is 0.8 moles. So therefore percentage equal to moles of product formed divided by moles of limiting reagent times 100, moles of reactant, that is limiting reagent, times 100. So it becomes 0.8 by 1 times 100 equals to 80%. So that's it for today. Thank you very much.